Alright, in this video we're going to talk about something called implicit differentiation, and it's going to be directly related to what we talked about in the last video about that respect rule and how we can apply the chain rule to take the derivative with respect to variables that are not present in our regular function. So here's an example of a type of problem that represents implicit differentiation. So if you've never seen an implicitly defined function before, that's what this is. So when we say implicitly defined function, it basically means we can't separate the x's from the y's. Okay, we can never get this function into something that looks like y equals a function of x. It just doesn't work. So because implicitly defined functions can have this property, it means they can have some pretty cool lines. So if I graph this particular function, it looks like this. Notice that this function fails the vertical line test pretty miserably, but it doesn't have to pass the vertical line test because it's not like y is a function of x. So whenever we put in one x input, we don't need to get one unique y output. We can actually get multiple y outputs. So therefore, implicit functions are pretty cool in that respect. However, what we can do is we can still find equations for lines tangent and normal to this particular line, and we do it by doing something called implicit differentiation. So if we go back here, if we are asked to find dy dx, basically what it's asking for is what is the derivative of y with respect to x given this particular function right here. All right. So the way that we can do this or figure this out is by what we can do is just how in algebra, how whenever you want to, let's say, if you do something to both sides of an equation, it's valid. So for example, if you subtract a number from both sides of the equations, if you divide both sides of the equation by something, if you raise both sides of the equation to a particular power, that's how we can solve for specific variables inside algebraic equations. And with derivatives, it's no different. So if we want to find dy dx, what we can do is take the derivative of both sides of the equation. Okay? So when we do this, we end up getting a method that we can isolate what dy dx is on its own and then solve an equation for what that is. So see if you can do that utilizing what we learned in the previous slides. This will be pretty difficult to do just as a first example problem, but just give it a shot anyway. All right, so if you've done it, if you take the derivative with both sides, you should get something which looks like this. Okay? So how did we get this? Where did all this stuff come from? Well, first of all, when we take the derivative of the product xy cubed, whoops, there we go. All right, if we take the derivative of the product xy cubed, that's going to be using the product rule. Okay, first we take the derivative of the first function x with respect to x. Again, realize that what we're taking derivative with respect to is exactly the same as the variable in the function. So we say, okay, buddy, we respect you. We don't have to add that dx over dx stuff to the end of that. So the derivative of x with respect to x is just 1. That 1 could we could put that right there. Then we multiply that by the second function, which is y cubed. So we get this. Now we keep the first function, which is x, the same, and we multiply it by the derivative of y cubed with respect to x. Remember, now we look at that respect rule. We say, okay, we're taking the derivative with respect to x. Y is not the same as x, so we say, oh, we get no respect. We add this stuff to the end of it. Okay, dy dx would be 3y squared, or I'm sorry, the derivative of y cubed with respect to y would be 3y squared. But then since we're taking the derivative with respect to x, we got to multiply it by this guy right down here. Now we take the derivative of x with respect to x, which again, what we're taking the derivative with respect to is the same as the variable, so we give it respect. We don't add all that stuff to the end of this one. So the derivative of negative x with respect to x is just 1. Now, hopefully you should start seeing the pattern. The derivative of 5y with respect to x, again, what we're taking the derivative with respect to, in this case the variable x, is not the same as variable y. So repeat everyone say it all at once. Oh, we get no respect. Okay, so we got to take the derivative and we got to add this dy dx to the end of it by the chain rule. Then the derivative of the constant 1 is just 0, so we're left with that. So with what we got right here, see if you can look at this and figure out how in the world would we get just dy dx out of all this stuff. Pause the video and see if you can figure that out. So if you were able to figure that out, or you weren't able to figure that out, what we can do is we can isolate everything with the dy dx to one side of the equation. So notice what I did is we have 3xy squared dy dx right here, and then we also have 5 dy dx right here. So what I can do is factor the dy dx out, and then we're just left with that. Now we also have a y cubed standing by itself and a 1 standing by itself. If I bring those over to the other side of the equation, I get 1 minus y cubed. So therefore, if I got that, I divide both sides of the equation by 3xy squared plus 5, and we're left with our final equation for what dy dx is. Notice this is different than any derivative equation we've seen before because it has both x's and y's inside of it. So the types of questions I could ask you with this might be something along the lines, okay, you don't like doing that? That's strange. Okay, just get out of here. Go over that way. All right. So the types of questions I could ask is, okay, well, at a specific x and y point on this curve, let's calculate the derivative. So at x equals -1, y equals 0. All we got to do is just plug those values into our equation right here. If we plug in 0 for y and -1 for x, we end up getting the slope of our line tangent to the curve as 1/5. What if we wanted an equation for a line tangent to the curve at this particular point? Well, we just use our point slope equation. We get y is mx minus a plus f of a. In this case, m is 1/5, a is -1, and f of a is 0. So we should get that in this case y is 1/5 times x plus 1 and then plus 0 on the end here. So let's see if that works. So let's go back to our Desmos graph here. And notice, hey, I got that point already right here. And here's the equation of that line with the point slope form. Check it out. It's the equation of a line tangent to the curve. It still works even for implicitly defined functions. So very, very cool. All right. So now let's look at another implicitly defined function. This one's a bit crazier. So get ready. Check that guy out. Okay. So that's a pretty nuts function. But it turns out, just as we did before, we can still find an equation for what the tangent line to that curve, or even what the slope of the line tangent to that curve is at any xy point on that curve. So let's do that as an example next. So coming over here, if we switch up our page, if we have this implicit equation, do exactly what you did. Rewind the video and rewatch the last exercise if you have to. This one's going to be pretty complicated, but again, the more complicated examples we go over, if you can get to understand these, then the simple ones we do on the quizzes and the tests are going to seem way easier than this. All right? So in this case, I've given you an implicitly defined function, so try to find dy dx on your own. All right, if you've given this a shot, the first thing you should have done was, first of all, take the derivative of both sides with respect to x, just like we did in the previous case. So we do that. If you didn't know to do that, pause the video right now, try to take that derivative, remember the respect rule, and give it a shot, then press play once you're done. All right, so if you tried this one out and took the derivatives of both sides with respect to x, you should have gotten something that looked fairly nasty, but something that looked like that. So let's look over how I got this, okay? First of all, we got to take the derivative of this side. Well, okay. We got to do the chain rule to do this because we have functions within functions here. So first we got to do the derivative of 1/2 sine, which is 1/2 cosine. We keep the inside the same. Now we do the derivative of the inside, okay? Remember, we are taking the derivative with respect to x. X is the same as x. So in that case, we give it respect. We don't add all that crap to the end of it. The derivative of x squared with respect to x is just 2x. However, when we take the derivative of y squared with respect to x by the respect rule, if we take the derivative with respect to x, x is not the same variable as y, so everyone say it with me. We get no respect. So we got to take the derivative of y squared with respect to y first, then by the chain rule multiply it by the derivative of y with respect to x. Again, it's the respect rule. The two variables don't match up. We give it no respect, so we add this crap to the end of it. Okay? So when we do the next side, again, we have the chain rule. The outermost thing we have is cosine. The derivative of cosine is negative sine. Now on the inside, if you weren't able to get this, pause the video real quick and see why I got this answer on the inside. Okay, if you figured it out or you haven't figured it out, you'll realize we got to use the product rule right here. We have one function x multiplied by another function y. So in this case, we take the derivative of the first. The derivative of x with respect to x is just 1, keeping y the same. That's why we have y. Then we keep x the same and multiply it by the derivative of y with respect to x. That's just a chain rule coming out, okay? So if you weren't able to get to this point on your own or you screwed this up, try the next step in this. Try to isolate that dy dx on itself. Remember what we did to do this. Basically, it was just algebra. We put everything with the dy dx on one side of the equation, everything without a dy dx on the other side. So try doing that and solving for dy dx right now. Okay, if you've given this a shot, what you should have gotten was something like this. All right. So again, we collect the like terms. We collect the terms with the dy dx in them. So we're going to get a 1/2 cosine x squared plus y squared multiplied by 2y dy dx. Realize the 1/2 and the 2 just cancel. So I'm left with just y times cosine of x squared plus y squared. Also over here we have a negative sine xy times x dy dx. That's why we have an x times sine xy over here. Again, it was negative on this side. If we want to bring it to the other side, it becomes positive. So now we've collected all the terms that are multiplied by dy dx, and all we're left with is 1/2 cosine x squared plus y squared times 2x. That goes over to this side. Realize it's negative because we got to bring it to the other side of the equation. Also realize the 2 and the 1/2 cancel each other when we multiply them out. Then we keep this negative sine xy times y right down here. So again, we've isolated everything with the dy dx in it on this side and everything without on this side. So if you weren't able to get to this step, there's just one more step you got to do to find dy dx. See if you can figure out what it is on your own. All right, so if you gave this a shot, you should have gotten this, okay? All we got to do now is to isolate dy dx. We just divide both sides of the equation by this big old guy right here, okay? So we get this nasty equation right here, and I could ask you a whole bunch of questions with this. What is the slope of the tangent line at this x value and this y value? But now that you have the equation for dy dx, you can figure that out. Now, the implicit differentiation problems we are going to look at least on the quizzes, are not going to be nearly this hard. They're a lot going to be more like the first one we looked at. However, on your worksheets, you are going to get some pretty tough implicit differentiation problems. So I would really recommend checking out these videos over again or doing example problems of implicit differentiation of the book if you want to get some more practice on this. So if you have questions, come to class tomorrow and ask them, and we'll go over a couple more examples.